On the morning of July 25, 1942, Lieutenant Commander Eddie Sanders walked across the tarmac at Naval Air Station San Diego toward an aircraft that should not have existed in American hands. The sun reflected off polished aluminum skin. The distinctive low-wing silhouette was unmistakable. The large red circle on the fuselage, though painted over with American markings, was still visible beneath the fresh paint. This was a Mitsubishi A6M Zero fighter, the aircraft that had terrorized Allied pilots across the Pacific for 8 months, and Sanders was about to discover something that would change the air war. The Zero, sitting on the North Island flight line, was not supposed to be there. Japanese pilots did not surrender their aircraft. They died in them, crashed them into the sea, or burned them on the ground rather than let them fall into enemy hands. The secrecy surrounding Japanese military technology was absolute. CTA placement. 145 words. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Allied intelligence had been trying for months to obtain an intact Zero for examination. They had wreckage from crash sites. They had fragments recovered from shot-down aircraft. But they had never possessed a complete, flyable Zero that could be taken apart, studied, and most importantly, flown against American fighters to understand its true capabilities and limitations. Sanders knew what the intelligence report said. The Zero could outturn any Allied fighter. It could outclimb them at low and medium altitudes. It had exceptional range, allowing it to escort bombers on missions that seemed impossible for a single-engine fighter. Japanese pilots used these advantages ruthlessly. They forced dogfights where their superior maneuverability meant Allied pilots died. The kill ratios in the opening months of the war reflected this brutal reality. For every Zero shot down, Japanese pilots were destroying 3, 4, sometimes 5 Allied aircraft, but reports and statistics told only part of the story. Sanders had spoken with pilots who had faced Zeros in combat. They described an aircraft that could turn inside anything they flew, that could climb away from trouble, that seemed to defy the normal limitations of fighter design. Some pilots claimed the Zero could almost hover during tight turns, hanging on its propeller while American fighters struggled to follow. The mystique had grown with each engagement, each loss, each mission where Zeros appeared and dominated. What the intelligence analysts wanted, what the tactical planners needed, what every Allied pilot in the Pacific desperately hoped for, was information about the Zero's weaknesses. Every aircraft had limitations. Every design involved compromises. The Zero's remarkable maneuverability and range had to come at a cost, but without an intact aircraft to examine and test. Allied forces were fighting blind, developing tactics based on combat reports and educated guesses, rather than engineering data and controlled flight testing. The aircraft Sanders approached that morning represented the answer to those questions. This Zero had crashed on Akutan Island in Alaska 5 weeks earlier. The pilot, Flight Petty Officer Tadayoshi Koga, had been part of a strike force attacking Dutch Harbor during the Japanese Aleutian Islands campaign. Engine damage, or possibly a combat wound, had forced him to attempt an emergency landing. He chose what appeared to be a flat, grassy field. It was actually a wetland covered in thick vegetation. When the Zero's wheels touched down, they dug into the soft ground. The aircraft flipped forward onto its back. Koga, still strapped in his harness, broke his neck. He died instantly, alone, on a remote Alaskan island. The Zero remained there for nearly a month, inverted, hidden in the grass, unknown to American forces. A Navy patrol from the seaplane tender USS Gillis finally discovered it during a search of Akutan Island. They reported finding an intact Japanese fighter. Naval intelligence immediately recognized the value. A recovery team was assembled, equipment was gathered, and on July 10, 1942, sailors used a barge and improvised lifting equipment to right the aircraft and transport it to Dutch Harbor, then to Seattle, and finally to San Diego for evaluation. To understand why this single aircraft mattered so much, it helps to know what the Zero represented in the summer of 1942. The war in the Pacific was going badly for the Allies. Japan had achieved a string of victories that seemed unstoppable. Hong Kong had fallen. Singapore, the fortress Britain claimed was impregnable, had surrendered. The Philippines were in Japanese hands. The Dutch East Indies, with their vital oil resources, were occupied. Burma was being overrun. Australia itself seemed threatened. At sea, Japanese naval forces had sunk the British battleship Prince of Wales and battle cruiser Repulse. They had devastated the American Pacific Fleet at Pearl Harbor. They had won the Battle of the Java Sea, destroying a combined Allied fleet. Japanese submarines ranged across the Pacific and Indian Oceans, sinking merchant ships and warships with alarming success. The strategic situation looked grim. The tactical situation, particularly in the air, looked even worse. Japanese pilots flying from carriers and island bases dominated the skies. The Zero fighter was the tip of that spear. Designed in the late 1930s by Mitsubishi's chief designer Jiro Horikoshi, the Zero reflected a specific design philosophy that prioritized performance over protection. Horikoshi and his team had been given demanding specifications by the Imperial Japanese Navy. The new fighter needed exceptional range to escort bombers on long overwater missions. It needed maneuverability to defeat enemy fighters in close combat. It needed climb rate to intercept enemy bombers. And it needed all of this while being light enough to operate from aircraft carriers with their limited deck space and catapult capabilities. Meeting these requirements meant making radical compromises. The Zero had no armor protection for the pilot, no self-sealing fuel tanks that could prevent fires when hit by bullets, no heavy-caliber weapons that would add weight. The airframe itself was built as light as possible, using special aluminum alloys and construction techniques that saved every possible ounce. The result was an aircraft that weighed 5,400 pounds empty, roughly half the weight of American fighters like the F-4F Wildcat. That low weight, combined with large wing area and a relatively powerful Nakajima Sakai 14-cylinder radial engine producing 940 horsepower, gave the Zero performance that seemed impossible. It could turn in a circle with a radius of less than 250 feet. It could climb to 20,000 feet in 7.5 minutes. It had a range of over 1,700 miles with drop tanks, allowing it to operate hundreds of miles from its base. In the hands of experienced pilots, men who had trained for years and fought in China, the Zero was devastatingly effective. Japanese naval aviation training was among the most rigorous in the world. Pilot candidates underwent years of instruction before they were considered combat-ready. They practiced formation, flying, gunnery, navigation, and air combat maneuvering until these skills became instinctive. Physical conditioning was brutal. Discipline was absolute. By the time a pilot earned his wings and was assigned to a carrier air group or land-based unit, he was a highly skilled professional warrior. These pilots flew their first combat missions over China starting in 1940. The Chinese Air Force, equipped with obsolete biplanes and early monoplane fighters, stood no chance. Japanese pilots achieved kill ratios of 10-1, 20-1, sometimes higher. They perfected their tactics against opposition that could barely fight back. They learned to trust their aircraft and to exploit its advantages ruthlessly. The Zero's reputation began to grow among Japanese aviators. It was superior to anything China could field. Many pilots began to believe it was superior to anything anyone could field. When war came to the Pacific on December 7, 1941, Zero fighters participated in the first wave of the Pearl Harbor attack. 43 Zeros provided air cover, shooting down several American aircraft attempting to respond. Not a single Zero was lost to enemy fighters. The pattern continued as Japanese forces swept south and west. Zeros operating from carriers and newly captured airfields destroyed Allied aircraft on the ground and in the air with brutal efficiency. Over the Philippines, American P-40 Warhawk fighters and P-35 fighters were outmatched. The P-40 was faster in a dive and at high altitude, but in the low altitude, turning fights that developed over Philippine skies, the Zero dominated. American pilots who survived these engagements reported that trying to turn with a Zero was suicide. The Japanese fighters could reverse direction, gain altitude, and position for another attack while American pilots were still completing their turn. Over Java and Sumatra, British Brewster Buffalo fighters and Hurricane fighters faced the same problem. The Buffalo, already considered obsolescent, was completely outclassed. The Hurricane, which had performed well in the Battle of Britain against German bombers, could not compete with the Zero in maneuverability. Dutch pilots flying Brewster Buffalos and older aircraft were massacred. In one engagement on February 19, 1942, Japanese aircraft, including Zeros, attacked Darwin, Australia, killing over 250 people and destroying 20 military aircraft. Allied losses mounted. The recovery of Koga's Zero from Akutan Island was not a simple operation. The island was remote, accessible only by sea or seaplane. Weather in the Aleutians was notoriously unpredictable, with fog, wind, and rain creating hazardous conditions. The recovery team that arrived in early July faced significant challenges. The Zero was inverted, partially buried in the soft ground. Its propeller was bent. The landing gear had collapsed. But the airframe appeared intact, and critically, the engine seemed undamaged. Lieutenant William Thies, an engineering officer from the Gillis, supervised the recovery. His team used hand tools and improvised equipment to dig around the aircraft, creating enough space to attach lifting cables. They brought wooden beams and metal brackets to construct a frame that could support the aircraft's weight without damaging the structure. On July 10th, after several days of careful work, they were ready to attempt the lift. The team used a combination of block and tackle rigging, hand-operated winches, and sheer physical effort to slowly raise the Zero. As it came upright, they inspected the damage. The propeller would need replacement. The landing gear required repair. Some skin panels were dented or torn, but the overall structure was sound. The engine, when they opened inspection panels, showed no obvious internal damage. This was extraordinary luck. Combat-damaged aircraft usually had catastrophic engine failures or structural damage that made them unflyable. Koga's Zero had simply flipped over during an emergency landing attempt. Everything else was intact. They loaded the aircraft onto a barge and transported it to Dutch Harbour, where Navy mechanics performed a preliminary inspection. What they found excited the intelligence officers present. This was not just an intact airframe, it was a complete weapons system. The two 7.7mm machine guns in the nose were undamaged. The two 20mm cannon in the wings were functional. The gun sight was intact. The radio equipment, though Japanese and incompatible with American systems, was present and could be studied. Even the pilot's manual and some navigation charts were still in the cockpit, soaked but readable after drying. From Dutch Harbour, the Zero was transported by ship to Seattle, then loaded onto a truck for the journey to Naval Air Station San Diego. The trip took days. At each stop, armed guards watched the covered aircraft. Naval intelligence wanted no information about this capture to leak. If the Japanese learned that an intact Zero was in American hands, they might change their tactics or modify their aircraft to address vulnerabilities they knew existed but assumed were secret. At San Diego, the Zero was taken to a secure hangar at the Naval Air Material Center. A team of engineers, mechanics, and test pilots gathered to examine it. They photographed every detail. They measured dimensions, weights, and structural members. They carefully disassembled components to understand their construction and materials. The engine was removed and placed on a test stand where mechanics could run it under controlled conditions while monitoring performance parameters. What they discovered during this examination was both impressive and revealing. The Zero's construction quality was excellent, riveting was precise, welds were clean, components fit together with minimal tolerances. The manufacturing reflected a high level of craftsmanship and attention to detail, but the design choices revealed the compromises Japanese engineers had made to achieve the Zero's remarkable performance. The skin thickness on the fuselage and wings was extraordinarily thin, averaging less than 1 millimeter in many areas. American engineers measured it at multiple points and were astonished. This thin skin saved weight but provided almost no protection against battle damage. A single .50 caliber machine gun round would tear through it easily. Even 30-caliber rounds would penetrate at close range. There was no armor plating anywhere except a small piece behind the pilot's head, and even that was minimal, just 8 millimeters thick. The fuel tanks were mounted in the wings and fuselage without any protection. They were simple aluminum containers, sealed but not self-sealing. Self-sealing tanks, which American and British aircraft used by 1942, contained layers of rubber that would swell and close bullet holes automatically, preventing fuel leaks and reducing fire risk. The Zero's tanks had none of this protection. A single incendiary round hitting a fuel tank would likely ignite it, and with the tank located close to the cockpit, the pilot would have almost no chance of survival. The control surfaces revealed another interesting design choice. The ailerons, which control the aircraft's roll, were large and relatively heavy. They were actuated by cables running from the control stick through pulleys to the aileron hinges. American engineers tested the control forces required to move these ailerons at rest. They were light, requiring minimal force. This would give the pilot excellent control authority at low speeds, contributing to the Zero's legendary maneuverability. But the engineers noted that control forces in flight would increase with airspeed due to aerodynamic pressure on the control surfaces. The wing structure itself was a marvel of weight-saving design. Horikoshi's team had used a minimum number of ribs and spars, relying on the skin to carry much of the structural load. This technique, called stressed skin construction, was not unique to the Zero, but Japanese engineers had taken it further than most designers dared. The result was wings that were incredibly light but also relatively flexible. Under high G loads, these wings would flex noticeably. Under very high loads, they might fail entirely. Engine. Examination revealed a reliable, well-designed radial engine. The Nakajima Sakae 12 produced 940 horsepower at takeoff power and could maintain 770 horsepower at 15,000 feet. It used a 2-speed supercharger to maintain power at altitude. Fuel consumption was reasonable, contributing to the Zero's exceptional range. The engine was air-cooled, eliminating the weight and complexity of a liquid cooling system, but also making it more vulnerable to battle damage. A single round through a cylinder could disable it. After 3 weeks of examination and preparation, the Zero was ready for flight testing. Mechanics had replaced the damaged propeller with a spare taken from captured equipment at Dutch Harbour. They had repaired the landing gear, replacing bent components and ensuring proper operation. They had filled the fuel tanks, checked the oil system, and verified that all control surfaces moved freely. On July 25, 1942, everything was ready. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Lieutenant Commander Eddie Sanders was chosen as the primary test pilot. Sanders was an experienced naval aviator with over 1,500 hours of flight time in various aircraft types. He had flown fighters, dive bombers, and patrol aircraft. He understood aerodynamics and aircraft performance. Most importantly, he could evaluate an aircraft objectively, noting both its strengths and weaknesses without letting preconceptions color his judgment. Sanders walked around the Zero that morning, conducting the external pre-flight inspection that every pilot performs before flight. He checked the control surfaces for freedom of movement and proper rigging. He examined the propeller blades for damage. He verified that the landing gear was secure. He looked for fuel leaks, oil leaks, or any other obvious problems. Finding none, he climbed into the cockpit. The cockpit was cramped by American standards, but not unreasonably so. The seat was simple, with minimal padding. The control stick was centrally mounted between the pilot's knees. The rudder pedals were adjustable for different leg lengths. The instrument panel contained the essential flight instruments: airspeed indicator, altimeter, artificial horizon, turn and bank indicator, compass, and engine instruments including tachometer, oil pressure, oil temperature, and fuel gauges. Everything was labeled in Japanese, but Sanders had been briefed on the layout and function of each instrument. Navy intelligence had provided translated diagrams of the cockpit. He spent several minutes familiarizing himself with the switch locations, control positions, and emergency procedures. The engine start procedure was straightforward, similar to other radial engines he had flown. Prime the cylinders, set the mixture, energize the magnetos, and engage the starter. The Sakai engine coughed, fired, and caught. Blue smoke puffed from the exhaust stacks as the engine warmed up. Sanders monitored the gauges, watching oil pressure rise and cylinder head temperatures climb into the normal range. The engine ran smoothly, with the characteristic deep rumble of a 14-cylinder radial. He tested the magnetos, checking for proper drop in RPM when switching from both magnetos to each individual magneto. Everything was normal. He cycled the propeller pitch control, verifying proper operation. He tested the flight controls, moving the stick and rudder pedals through their full range of motion, while observers outside confirmed that the control surfaces responded correctly. Satisfied that the aircraft was airworthy, Sanders taxied to the runway. The Zero handled normally during taxi, steering easily with rudder and differential braking. Visibility over the nose was adequate, better than some tailwheel aircraft he had flown. At the runway threshold, he performed a final check of engine instruments, control positions, and flight instruments. Tower cleared him for takeoff. Sanders advanced the throttle smoothly to takeoff power. The Zero accelerated quickly. The tail came up almost immediately, improving forward visibility. At 65 knots, Sanders pulled back gently on the stick. The aircraft lifted off smoothly, climbing at what felt like an impressive rate. He retracted the landing gear, which operated normally, and reduced power to climb power. The rate of climb indicator showed over 3,000 feet per minute. This matched the reported performance data. The Zero climbed like nothing Sanders had flown before. At 5,000 feet, Sanders leveled off and began basic handling checks. He flew straight and level, noting the control forces and aircraft stability. The Zero was stable but responsive, requiring minimal control input to maintain altitude and heading. He initiated a gentle turn, banking, 15 degrees to the left. The aircraft responded immediately to control input, rolling smoothly into the turn. He reversed the turn, rolling right. Again, the response was immediate and predictable. He increased the bank angle to 30 degrees, then 45 degrees. The Zero turned in remarkably tight circles. The turn radius was noticeably smaller than American fighters at the same speed and altitude. Sanders could see why Japanese pilots favored turning engagements. In a sustained turn at moderate speeds, the Zero had a decisive advantage. Any American fighter trying to match this turn rate would either stall or lose altitude rapidly. But Sanders had not been sent up just to confirm what everyone already knew. His mission was to find weaknesses, to identify limitations that could be exploited tactically. He climbed to 10,000 feet and began testing the aircraft at higher speeds. He accelerated to 150 knots, then 180 knots, then 200 knots. At each speed, he performed the same basic handling tests, noting how the aircraft responded. At 150 knots, the controls still felt light and responsive. At 180 knots, he noticed the controls becoming heavier, requiring more force to achieve the same control deflection. This was normal. Aerodynamic forces on control surfaces increase with the square of airspeed. What worked at 100 knots required 4 times the force at 200 knots. At 200 knots, Sanders attempted a roll to the right. He pushed the stick firmly to the right, applying the force he estimated would be needed based on his experience with other aircraft at this speed. The Zero responded, but slowly. Very slowly. The roll rate was perhaps 1/3 what he expected. He pushed harder on the stick, applying more force. The aircraft rolled right, but the rate remained disappointingly slow. The ailerons felt mushy, not giving the crisp response they had, shown at lower speeds. He rolled left to return to wings level, then attempted another roll to the right. Same result. The aircraft would roll right, but only reluctantly, requiring significant stick force and producing a sluggish roll rate. He repeated the test several times, varying his technique and the amount of force applied. The result was consistent. Above 200 knots, the Zero's roll rate to the right degraded significantly. Sanders continued testing, pushing the speed higher. At 220 knots, the problem became more pronounced. At 240 knots, rolling right was nearly impossible. The stick forces required were enormous, and the actual roll rate achieved was glacially slow. Rolling left remained acceptable, though also degraded from low-speed performance. But the asymmetry was striking and significant. After 40 minutes of flight testing, Sanders landed the Zero and immediately requested a meeting with the engineering team and intelligence officers. What he had discovered was not just interesting, it was tactically exploitable. The Zero had a specific, repeatable weakness that could be used against it in combat. Above 200 knots, the aircraft could not effectively roll right. Any American fighter that could maintain speeds above 200 knots in combat would have an enormous advantage. The engineering team wanted to understand why this weakness existed. They returned to the captured Zero and examined the aileron system more carefully. What they found explained everything. The ailerons were cable-actuated, with cables running from the control stick through fairleads and pulleys to the aileron hinges. These cables had a small amount of stretch under load. At low speeds, with low aerodynamic forces on the ailerons, this stretch was negligible. The system worked perfectly. But at high speeds, the aerodynamic forces on the ailerons increased dramatically. The right aileron, which had to move upward to initiate a roll to the right, faced especially high forces because it was deflecting against the airflow. The cables stretched under this load, the pulleys flexed, the entire control system deformed elastically. The pilot would push the stick right, applying force, but much of that force went into stretching cables and flexing components, rather than actually deflecting the aileron. Additionally, the large aileron area that provided such excellent low-speed control became a liability at high speed. The aerodynamic forces trying to resist aileron deflection were proportional to the square of the airspeed and the size of the control surface. The Zero's large ailerons, combined with its flexible cable control system, created a situation where the control forces became excessive at speeds above 200 knots. American fighters of the same era had different control systems and different design priorities. The F-4F Wildcat and the newer F-6F Hellcat used pushrod control systems for the ailerons, which were much stiffer than cables. These systems had less flex under load. The ailerons themselves were smaller relative to wing area, trading some low-speed maneuverability for better high-speed control. Most importantly, American fighters were designed to fight at higher speeds, where engine power and dive performance mattered more than low-speed turning ability. The tactical implications were immediately clear to the intelligence officers analyzing Sanders' report. American pilots should avoid slow-speed turning engagements where the Zero excelled. Instead, they should use hit-and-run tactics, diving from altitude, making a high-speed attack, and then using their superior diving speed to escape. If a Zero attempted to follow, the American pilot should roll right while maintaining high speed. The Zero would be unable to follow effectively, giving the American pilot time to extend away, regain altitude, and set up another attack. This tactical approach was not entirely new. Commander John Thatch, leading fighter squadron commander at the Battle of Midway in June 1942, had already developed a defensive tactic called the Thatch Weave. Two American fighters would fly as a pair, weaving back and forth. When a Zero attacked one fighter, the other would turn toward the threat, forcing the Zero to break off or face a head-on attack. The tactic worked by denying the Zero the sustained turning engagement it needed to bring its superior maneuverability to bear. But Thatch's tactic was defensive, designed to protect American fighters from being shot down rather than to shoot down Zeros. The information from the captured Zero allowed development of offensive tactics. American fighters could now dictate the terms of engagement, using their strengths against Japanese weaknesses. The Zero's poor high-speed roll rate to the right became its Achilles heel, a vulnerability that skilled American pilots could exploit ruthlessly. Naval Intelligence compiled Sanders' test flight report along with the engineering analysis and distributed it throughout the Pacific Fleet. The document was classified secret, with distribution limited to fighter squadron commanders and their pilots. The report was detailed and specific. It provided exact performance data at various speeds and altitudes. It described the Zero's strengths honestly, acknowledging the aircraft's superior low-speed maneuverability and climb rate. But it also detailed the weaknesses, particularly the high-speed aileron problems and the lack of armor protection. Fighter squadrons received tactical bulletins based on this information. The guidance was clear and actionable. Never dogfight a Zero at low speed. Use altitude advantage to set up high-speed diving attacks. Attack from astern or from the side, using brief firing passes. Do not attempt to follow a Zero in a sustained turn. If attacked, roll right at high speed to evade. The Zero cannot follow effectively. Use superior diving, speed to extend away from the fight, then regain altitude advantage for another attack. Marine Corps fighter squadrons operating from Henderson Field on Guadalcanal received this information in late 1942. Marine pilots flying F-4F Wildcats had been suffering heavy losses against Japanese Zeros based at Rabaul. The tactical bulletins changed everything. Pilots who had been fighting defensively, trying to survive against a superior opponent, now understood they had advantages they could exploit. The Wildcat was slower than the Zero in level flight and could not match its turn rate. But the Wildcat could dive faster, had better high-speed handling, and was far more rugged, with armor protection and self-sealing fuel tanks. Marine pilots adjusted their tactics accordingly. They patrolled at altitude, watching for incoming Japanese formations. When Zeros appeared, escorting bombers toward Guadalcanal, the Marines dove from above, building up speed, then made quick firing passes through the Japanese formation. If Zeros attempted to engage, the Marines rolled right and dove away, using the Zero's high-speed limitations against it. Kill ratios began to shift. By early 1943, Marine pilots were destroying Zeros at rates that would have seemed impossible 6 months earlier. Navy fighter squadrons aboard carriers implemented similar tactics. The F-6F Hellcat, which entered service in January 1943, was specifically designed to fight Zeros using the lessons learned from the Akutan Zero. The Hellcat was fast, reaching 380 miles per hour at 17,500 feet. It could dive even faster, maintaining control at speeds where the Zero's ailerons became almost useless. It had excellent visibility from the cockpit, allowing pilots to spot threats and targets more easily. And it was tough, with armor plating, self-sealing fuel tanks, and a structure that could absorb tremendous battle damage and still bring the pilot home. Hellcat pilots trained specifically in boom and zoom tactics. They practiced high-speed approaches, quick-firing passes, and rapid disengagements. They learned to recognize when a Zero was trying to draw them into a turning fight and to resist that temptation. The results were dramatic. The F-6F Hellcat achieved a kill ratio of 19-1 against Japanese aircraft during the war. Much of this success came from superior pilot training, better tactics, and overwhelming numerical superiority. But the aircraft itself was designed around the knowledge gained from testing the Akutan Zero. Japanese pilots, meanwhile, continued flying Zeros largely unaware that Americans understood their aircraft's limitations in such detail. Japanese intelligence knew the Akutan Zero had been captured. Reports reached Tokyo about an intact Zero found in Alaska, but the Japanese High Command did not know the aircraft had been restored to flying condition, extensively tested, and used to develop specific counter-tactics. Japanese pilots continued to employ the tactics that had worked so well in 1941 and early 1942, forcing turning engagements and relying on superior low-speed maneuverability. These tactics became progressively less effective as American pilots learned to refuse the turning fight. Japanese pilots reported with frustration that American fighters would no longer engage on Japanese terms. The Americans would dive, shoot, and run. They would not stay and fight. From the Japanese perspective, this seemed cowardly. From the American perspective, it was simply intelligent use of their aircraft's strengths against the enemy's weaknesses. The mystique of the Zero began to fade. What had seemed invincible in 1942 looked increasingly vulnerable by 1943. The Akutan Zero itself continued to serve American interests throughout the war. After Sanders' initial test flights, other pilots flew it, including comparison flights against various American fighter types. Engineers continued to study it, examining every aspect of its design and construction. The aircraft was eventually damaged beyond repair during a landing accident in February 1945 at NAS San Diego. By then, it had served its purpose. The knowledge gained from testing it had been incorporated into American fighter tactics, training programs, and aircraft design. The Zero was no longer mysterious. It was understood. For Japanese pilots still flying Zeros in 1945, the situation was desperate. The aircraft they flew was essentially the same as the one that had dominated the skies in 1942. Some improvements had been made. Later variants had slightly more powerful engines, modified exhaust systems for additional thrust, and in some cases heavier armament. But the fundamental design remained unchanged. The Zero was still light, maneuverable, long-ranged, and fatally vulnerable to damage. American fighters, by contrast, had evolved significantly. The F-6F Hellcat was being supplemented by the F-4U Corsair, an even faster and more powerful fighter. The P-38 Lightning, P-47 Thunderbolt, and P-51 Mustang were dominating the skies over various Pacific battlefields. All of these aircraft could outrun the Zero. Most could outdive it. All had superior firepower, better protection, and more robust construction. Japanese pilots faced overwhelming material disadvantage. The contrast reflected broader industrial realities. American factories produced over 99,000 fighter aircraft during World War II. Japan produced approximately 30,000, and many of these were obsolete designs retained in service because nothing better was available. American pilots received extensive training, often accumulating hundreds of hours of flight time before seeing combat. Japanese training programs, strained by fuel shortages and the loss of experienced instructors, produced pilots with minimal preparation. By 1944, some Japanese pilots were being sent to combat units with less than 100 hours total flight time. The psychological impact on Japanese pilots was significant. Men who had trained for years and fought successfully in China and the early Pacific campaigns understood they were flying obsolete aircraft against overwhelming odds. They knew American fighters were faster, tougher, and more heavily armed. They knew American pilots had better training, more experience, and unlimited ammunition and fuel. Some Japanese pilots, particularly the experienced veterans who had survived years of combat, adapted their tactics as best they could. They avoided engaging superior American fighters when possible. They focused on attacking bombers, where their cannon armament was effective. They used clouds, terrain, and surprise to offset their disadvantages. But for most Japanese pilots, especially the inexperienced replacements being rushed into combat in 1944 and 1945, survival was unlikely. The Zero that had once seemed invincible had become a death trap. Its lack of armor meant any hits were likely fatal. Its unprotected fuel tanks meant fire was almost inevitable when damaged. Its light structure meant it could not absorb battle damage the way American fighters could. Pilots died not because they lacked courage or skill, but because they were fighting in aircraft that were fundamentally inadequate for the war they faced. The story of the Akutan Zero is often told as a tale of intelligence, success, and tactical adaptation. It is those things. But it is also a story about design, philosophy, and the consequences of specific engineering choices. Japanese designers created the Zero to meet specific requirements: long range, excellent maneuverability, and lightweight. They succeeded brilliantly at meeting those requirements. The Zero was exactly what it feared, was designed to be. But the war it was designed for, the war against China and potentially the Soviet Union, was not the war Japan actually fought. Against American industrial capacity, American pilot training systems, and American tactical adaptation, the Zero's advantages proved insufficient to offset its vulnerabilities. The aircraft that dominated the Pacific skies in 1942 was obsolete by 1944, not because it had changed, but because everything around it had changed. American fighters became faster, tougher, and more powerful. American pilots learned to avoid the Zero's strengths and exploit its weaknesses. American tactics evolved from defensive survival to offensive dominance. The morning Lieutenant Commander Eddie Sanders climbed into that captured Zero and discovered it could not roll right above 200 knots. He found more than a technical limitation. He found the answer to a question that had haunted Allied pilots since Pearl Harbor. The Zero was not invincible. It was not even particularly good at high-speed combat. It was a specialized tool, optimized for specific conditions, and those conditions were not the ones that characterized most Pacific air combat after 1942. The mystique was just that. Mystique, not reality. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.